Good day everyone, I am MUTIA. In today's video, we are going to tackle about a simple precipitation method to synthesize zinc oxide nanoparticles using zinc nitrate and urea in aqueous solution.
Hi there, this is Adrian Moy. The precipitated compound was calcined and characterized by the researchers using powder X-ray diffraction, thermogravimetric analysis, scanning electron microscopy, transmission electron microscopy, Fourier transformation infrared spectroscopy, and UV-vis spectroscopy technique.
Also, we're going to review a scientific journal entitled Facile Synthesis of Nano-sized Zinc Oxide by Direct Precipitation Method that was published in January 2013.
In the last 15 years, more than 50,000 papers have been titled ZnO that have been recorded in international scientific indexing. Its outstanding popularity is due to its multifunctionality. ZnO is a unique and important inorganic material that has sparked a lot of interest due to its unique properties and innovative application in a variety of fields: semiconductivity, piezoelectricity, pyroelectricity, catalysis, optoelectronics, and powder metallurgy are only a few of the properties it possesses. Furthermore, optoelectronic, catalytic, and photochemical properties of xenon nanoparticles are influenced by their optical properties. Material scientists all over the world have recently used a variety of methods to prepare ZnO powder and thin films with a variety of morphologies and regulated growth, which was stimulated by the fact that its properties are highly dependent on size, shape, and orientation ratio, including chemical vapor disposition, electrodisposition, hydrothermal, electrochemical, solution combustion, salt gel, vapor liquid solid phase, pulse laser disposition, and precipitation. Precipitation and the salt gel process, among all methods, have the best control over particle nucleation, aging, and growth in solution. Direct precipitation is a simple and cost-effective method for mass material processing. Particle growth is owed to interaction between different aqueous solutions in this method, which results in the formation of very small particles. Since small particles with low solubility dissolve and reprecipitate on the surface of a larger particle in solution, agglomeration occurs in the solution as the particles clog together to reduce surface energy.
This study was designed to use urea as a precipitating agent in a simple and cost-effective direct precipitation method to synthesize zinc oxide nanoparticles. Also, the precipitating agent will help to control particle size and dispersion in the solution, as well as calcination expansion. Materials and equipments. The zinc nitrate and urea were bought from Fischer Scientific, Germany, and utilized with no further purification. Double distilled water was used to prepare precursor solutions. Zinc oxide nanoparticles were synthesized using zinc nitrate and urea as precursors in a direct precipitation process. Figure 1 shows the thermogravimetric analyzer SDTA851E from Mettler Toledo and was utilized during the thermogravimetric analysis. As reflected in Figure 2, powder X-ray diffractometer D8 Advance from Bruker was utilized during X-ray diffraction or XRD. Figure 3 shows two different microscopes that were used to measure the particle size and morphology of zinc oxide nanoparticles, transmission electron microscopy, and scanning electron microscopy. Bruker FTIR spectrometer tensor 27 was also used in Fourier transformation infrared spectroscopy. And lastly, Mettler-Toledo spectrophotometer will be used in the UV-Vis absorption spectra. The schematic diagram depicts the chemical reactions to synthesize zinc oxide nanostructure. In a standard synthesis, 0.5 molar concentration of zinc nitrate was dissolved in 50 ml distilled water and stirred continuously for 30 minutes to complete dissolution. In 50 ml of distilled water, 1 molar concentration of urea was also prepared with continuous stirring for 30 minutes. To allow complete growth of nanoparticles, urea solution was used as a precipitating agent and was added dropwise into zinc nitrate solution with vigorous stirring at 70 degrees Celsius for 2 hours. The final precipitating solution became cloudy and whitish. To remove any impurities or potential absorbed ions, the white precursor product was centrifuged at 8,000 rpm for 10 minutes before being washed with distilled water. The obtained product was calcined in a muffled furnace at 500 degrees Celsius for 3 hours in an air atmosphere. With a combination of analytical techniques, we can determine or confirm the molecular structure for a chemical entity. Using a thermogravimetric analyzer in the temperature range 30 to 800 degrees Celsius at a heating rate of 5 degrees Celsius per minute under nitrogen atmosphere, the synthesized zinc oxide was subjected to thermogravimetric analysis. Powder X-ray diffraction patterns were obtained for synthesized samples using a powder X-ray diffractometer with copper K-alpha radiation, operating at 30 megaampères and 40 kilovolts to determine the crystal phase identity and estimate the crystallite scale. Transmission electron microscopy and scanning electron microscopy were used to measure the particle size and morphology of zinc oxide nanoparticles. A Bruker FTIR spectrometer was also used to obtain Fourier transform infrared spectra on potassium bromide pellets at room temperature. In the transmission mode, FTIR spectroscopy provides qualitative details about how adsorbed molecules are bound to surfaces as well as structural information about solids. And lastly, a Mettler-Toledo spectrometer was used to record the UV-Vis absorption spectra. The nanoparticles were dispersed in ethanol and syndicated for uniform dispersion before UV-Vis calculation.
In Figure 5 shows the powder XRD pattern for the synthesized compound, which is calcined at 500 degrees Celsius, obtained by direct precipitation of 0.5 molar concentration of zinc nitrate and 1 molar concentration of urea. With copper K-alpha radiation, the XRD peak has a wide angle range of 2 theta from 10 to 90 degrees. The powdered XRD pattern were indexed to a pure hexagonal structure with A equals to 32 and C equals to 5.2 lattice parameters, and a space group of P63MC as shown in Figure 5. The peaks are at 31.76, 34.42, 36.25, 47.53, 56.59, 62.86, 66.37, 67.94, 69.08, 72.95, 81.38, and 89.61 degrees correspond to the pure ZnO. It has the same match with the GCPDS Joint Committee powder diffraction standard with a match card number of 01-79-0206, indicating that the ZnO particles have a crystallized structure. The Davis-Kerr equation was used to measure the average crystalline size. D is equals to K alpha over beta cos theta, where D is the crystallite size, diameter, and K is the form factor, which typically value is 0.9. Alpha is the incident beam wavelength, and B is the diffraction line broadening measurement in radians at half of its own maximum intensity. And theta is the Bragg angle. The average crystallite size was found to be 35 nanometer using XRD data in the calcite compound. No other peaks were found, indicating that the formation of pure hexagonal structure of ZnO. Thermal analysis was carried out in a temperature range of 30 to 800 degrees Celsius to determine the decomposition and phase formation that occurs during heat treatment of the as-prepared compound. TGA was carried out on as-prepared compound by heating it in an alumina crucible in air at 5 degrees Celsius per minute. The thermal activity of the as-prepared compound obtained by direct precipitation of 0.5 molar concentration zinc nitrate and 1 molar concentration of urea is shown in Figure 6. In a temperature range 30 to 150 degrees Celsius and 160 to 450 degrees Celsius, there are two pronounced mass loss steps in TG curve. The first weight loss is mostly due to evaporation of surface absorbed water, while the second is due to the volatilization and combustion of organic compound in the sample. The first step of mass loss was gradual and took place between 30 and 150 degrees Celsius. The removal of surface absorbed water from aqueous urea and nitrate solution resulted in a mass loss of 18.9%, which was due to the removal of absorbed water. The main mass loss occurred between 160 to 450 degrees Celsius with a weight loss of 32.6% due to the volatilization and combustible organic species found in the sample. In the TGA curve, there is no signal associated with these latter thermal events, confirming the crystallization and phase transition event of ZnO nanoparticles. In Figure 7 shows electron photomicrograph of ZnO nanoparticles formed by direct precipitation of 0.5 molar concentration of zinc nitrate and 1 molar concentration of urea at 500 degrees Celsius for 3 hours. Some images of ZnO nanoparticles are shown in Figure 7a, and it was found that the particles were defined and small spherical shape with agglomerated particles, while in Figure 7b shows 10 images. The ZnO particles were found to be 30 to 50 nanometer range after a 3-hour heat treatment at 500 degrees Celsius. ZnO nanoparticles are mostly granules with a small spherical shape and are well crystallized, as can be seen in Figure 7b.
During the precipitation phase, infrared spectroscopy was used to detect the presence of functional groups absorbed on the surface of synthesized nanoparticles. Figure 8 shows the FTIR spectra of zinc oxide powder obtained by calcining at 500 degrees Celsius for 3 hours with 0.5 molar concentration of zinc nitrate and 1 molar concentration of urea. The absorption peak was observed in the range of 3,200 to 3,600 wave number as shown in Figure 8. For recording UV-Vis spectra, the sample of zinc oxide solution was prepared by ultrasonically dispersing them in absolute ethanol. The absorption peak in Figure 9 corresponds to a zinc oxide sample that was calcined at 500 degrees Celsius and showed strong absorption in the wavelength of 378.3 nanometers. The intrinsic band gap absorption of zinc oxide due to electrons transfer from the valence band to the conduction band can be attributed to this. Furthermore, the XRD and TEM results indicate that the zinc oxide particles are 30 to 50 nanometers in size.
The researchers conclude that the nano-sized ZnO particles were successfully produced using the direct precipitation method in aqueous solution with zinc nitrate as the zinc source and urea as the precipitating agent. The produced ZnO powder had a size range of 30 to 50 nanometers, according to the XRD analysis. TJ revealed that the sample contains NO-2, CO, CO2, and H2O. The SEM analysis showed that the particles had a spherical morphology, while the TEM images confirmed that ZnO nanoparticles have a small, spherical shape and are well crystallized in nano-size range of 30 to 50 nanometers. In the uncalcined sample, the FTIR spectrum reveals the presence of OHCO2, NO-2, and CO group. The band gap of synthesized ZnO nanoparticles was lower than that of the bulk ZnO nanoparticles. As the result, the direct precipitation method of synthesis of ZnO nanosized particles is simple, fast, and environmentally friendly.
Researchers found that using urea as a precipitating agent in a simple and cost-effective direct precipitation method to synthesize zinc oxide nanoparticles was efficient. The approach and findings were also sufficiently validated by the theoretical background provided. In terms of the methodology, the structural characterization of zinc oxide nanoparticles was determined and verified using a combination of analytical techniques which confirmed the molecular structure of the particles, morphology, and the existence of different compounds. As for the results, the direct precipitation method was used to successfully generate nano-sized zinc oxide particles in this analysis. Based on the current scientific facts and hypotheses, conclusions and assumptions were accurately inferred. Finally, the MLA formatted citations that were used by the researchers in the study were well structured.